Welcome to the 8th week of the course. In this week, we will learn some advanced. This is the first week where we will learn some advanced tools in parameterized complexity, and in the next 3 to 4 weeks, we will see tools such as important separators, some algebraic techniques, advanced way of doing dynamic programming, and some matroid-based techniques. Okay. So just to start with, let's start with an example. So the tricks and techniques that I'm going to teach this week is about important separator. But before we even reach important separators, let's talk about vertex cover. Okay. So what is a vertex cover? So vertex cover is like input is gk, or let's ask a very different questions. So suppose if I ask the following question, how many minimal vertex covers of size at most k are there? The 2 power k branching algorithm, right? You take an edge uv and you branch g minus a, comma k minus 1, g minus v, comma k minus 1, starting with g comma k, actually tells you that the number of such objects are upper bounded by 2 to the power k. So the number of minimal vertex covered are at most 2 power k. Now you may ask, what is minimal vertex cover? So of course, minimal vertex covered of size at most k. So what is the minimal vertex cover of size at most k? A set X subset of Vg is called minimal vertex cover of size at most k. What property is this? First, cardinality of X is at most k. Secondly, G minus X is an independent set. And finally, no subset of X, in fact proper subset of X, no proper subset of X intersects all edges. Or in other word, for all X prime proper subset of X, G minus X prime is not an independent set. Right? So this is why it is minimal, meaning no proper subset does the job of our requirement, is not an independent set. Okay. So we would like to ask, for several problems, the problem in between is about number of min cuts or number of minimal cuts between two vertices, right? So if you recall correctly, in the algorithm for odd cycle transversal, after doing iterative comparison, we reduced the problem to finding a minimum cut. But maybe for many, we don't know whether, for a problem, we don't know whether it contains a minimum cut, but we might be able to show that there exists a min cut. But so let's ask ourselves, so this is a combinatorial question. Okay. So what is our combinatorial question? Say input is graph G, two vertices S and T, okay, and an integer K, and the question, how many ST edge cuts, okay, how many minimal ST edge cuts are minimal ST edge cuts of size at most k are there. So what is the meaning of minimal ST edge cuts? It's like you are given a graph ST, okay, edge cut basically means this is the sum set of edges, say S. So moment if we delete S from G, there is no path between S and T, or in other words, okay, or in other words, in G minus S, S and T belong to two different connected components, or two different connected components, right? So such S are called edge cuts, or okay. And what is the minimum ST cut and edge cut of minimum size? Okay, we will. And what is the minimal ST cut? Minimal. Okay, a minimal ST cut is, first of all, a minimal ST cut of say size at most k is, first of all, so a minimal ST cut say S of size k is basically, first, cardinality of S is at most k. Secondly, S is an edge cut. And thirdly, no proper subset of S is an edge cut. In other words, for all S prime proper subset of S, S and T belong to the same connected component, in G minus S prime. That's it. So these are called minimal ST. So now if I ask ourselves in a graph, how many minimal ST cuts of size at most k are there? So you notice, if my graph is consisting of some S and T, and suppose this is a vertex disjoint paths, okay, these are vertex disjoint paths. And how many such paths are there? Well, let's say there are like k such paths, right? And each path has n by k number of edges. Okay, so we have path say p1 dot 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 pk, and each path has size say n by k edges in terms of edges. Okay, now notice these are edge disjoint paths. There are k edge disjoint paths. So any min cut or any minimal cut must contain at least one edge from here. And notice, for any minimal cut, once you pick one edge, any other edge is redundant. So for this example, number of minimum ST cuts, okay, is same as number of minimal ST cuts, of course, of size at most k, of size at most k. In fact, this is exactly equal to it. And this is obtained by what? From each path you pick, you have a choice of any one edge. The moment you pick one edge, you are done. So this is like we have a n by k to the power k, right? So unlike say vertex covered, number of minimal ST cuts, are upper bounded by, number of minimal ST cuts are upper bounded only by some function of n, right? And not a function of k alone. Okay. Now you might ask, where do we require these kind of Like why do we care about minimal ST cuts and all this? So as I said to you before, if we could have been able to bound number of minimal ST cuts by just a function of k, for many problems we could enumerate this minimal ST cuts and reduce the problem to us with a smaller parameter. We will see some examples in this lecture. But for now, all I wanted to tell you that the number of minimal ST cuts of size at most k is not upper bounded by k. We could have also done the same thing with respect to vertices, but for this lecture series, we will only concentrate on edge cuts and we will not concentrate on vertex cuts. Okay. So I will follow the slides by Professor Daniel Marks. It is an old slides and it is titled Important Separators and Parameterized Algorithms. And so I have just kept it the way so that there's a proper accreditation to his slides. Okay. So the main message we will try to give: small separators in graphs have interesting extremal properties, and we could exploit that for combinatorial and algorithmic games. So what are we going to tell you? We are going to bound the number of important cuts. So we also need to define what is an important cut and how we can bound this, and then show its application in designing FPT algorithm for the problem called multi-way cut and directed feedback vertex set. It can also be applied in something called PQ clustering, but we will not be teaching you in this course. However, you can find that in the textbook. Okay, and this is based on what is a new technique which led to several new algorithmic development on the cut problems, what is called random selection of important separators. But again, we will not talk about it. And this notion of important cuts, I have only been talking about minimal separators in undirected graph, but it could also be defined for directed graphs. It could also be defined for the vertex version, in the sense that I have S and T, and I would like to delete minimum number of vertices to disconnect S from T. And then we can ask, what is the minimal number of vertex separators? But as I said before, we will focus on edge cuts in this week course. Okay. So let me define. So I'm going to define a notion of boundary edges. So what is a boundary? So you give me a set R of vertices. By delta R, I will mean set of edges that leaves R, meaning it contains exactly one endpoint in R. So for example, look at, if this is my R, you see here, this set of vertices are R, then the red colored edges are my delta R. Okay. And a set S of edges is a minimal XY cut. So X is a set of vertices, Y is another set of vertices. If there is no XY path in G minus S and no proper subset of S breaks every XY path. Okay. So what is a minimal XY cut? So the way we defined before, a minimal ST cut, now S has been replaced by a subset of vertices called X, T has been replaced by a subset of vertices Y, and our objective is to find a set of edges which disconnects X from Y, or in other words, when we delete this set of edges, there is no path from X going to Y. So for example, if this yellow color is X and this yellow color is X and this yellow color is Y, then if I delete the edges going across this R, then there is no path from X to Y. Okay. And an important observation is that every minimal XY cut S can be expressed as S equal to delta R for some X subset of R and R intersection Y is phi. Why? So let's try to prove this lemma just to get a feeling for how these things are done. Okay, so here it is. So suppose after I delete G minus S, how does the world look like? Here is my component that consists of X, okay, and everything else, okay. But notice that this set of this components may not be containing X alone. So this is basically minimum set of components that contains X. Okay. Or in other words, let's see. So I delete G minus S. How it will be? Suppose this is this. Okay. And suppose, what are these? These are vertices of, say, some piece of X. This is some piece of X. This is also some small piece of X. This is also a small piece of S. This is small piece of Y. This is. Now notice, ideally, I would like R to be, this is my R. Okay. Notice that your minimal cut, if it is a minimal cut, right? If it is a minimal cut, okay. So if I take this, you may ask, well, does a minimal cut, since it is a minimal cut, minimal, like it's so definitely I can disconnect X from Y by deleting edges incident to R. So now you can definitely, right? But maybe there is an edge here, there is an edge here. But notice, then R is not a minimal cut, because even if I delete these edges, right? I delete these edges, then I have a set of edges whose deletion disconnect X from Y, which implies that whenever you have a minimal cut, you can find a set R such that in that R, all the vertices of X are there and the vertices of Y are in the complement, and the set of edges which you are looking for is the set of edges which are in the boundary of R. Okay. So you can prove this. So I just gave you a small hint how to go about proving this observation. Okay. So every minimal XY cut can be expressed as like set of edges emanating out of some R that contains X completely and which is disjoint from Y. Okay. Okay. And it is a well-known theorem that a minimum XY cuts can be found in polynomial time. Okay. And the size of minimum XY cuts equal the maximum size of pairwise disjoint collection of XY part. This is nothing but our classical Menger's theorem, right? And a minimum XY cut can be found in polynomial time, and this is again using max flow min cut theorem. Okay, so these are classical algorithm that is being taught in our undergraduate algorithm. Okay, so we will not be telling you the proof for this. Okay, but we will give you some idea how people actually go about proving it, because we will need some of these basic concepts also for the set of objects, so the tools which we need for our purpose. Okay, so there is a long list of algorithms for finding disjoint paths and minimum cuts. There is an algorithm by Edmonds Cart, Denise, Puss-Level, Orlin King, Rao Tarjan. Okay, but for our purposes, all we need is the following: an XY cut of size at most k, if exists, can be found in time k times m plus n. So if you notice, this is for fixed k, this is linear time algorithm, right? And by linear, what do we mean? Linear, we mean order m plus n, where m is number of edges, n is number of vertices. Okay, okay, and k is the cut size. And how do we actually find such an algorithm? Is very tried. So we try to grow a collection P of edge disjoint XY paths. Okay, and at any point of time, so suppose this is an original graph. Okay, and we construct what is called residual graph in the residual graph, the edges which are not used are bidirectional, meaning it can be used in both ways. So you can simulate this either by, you can simulate these unused edges by putting a 2 cycle or putting an edge in both directions. So for example, this, and the edges which are used by your flow or used by your path, you put in the direction from y to x. So for example, this edges on this red things are oriented from y to x. Okay, so this is what is called residual graph, and you must have seen this in your, when you were designing max flow min cut algorithm. So at any point of time, you are given some set of edges, you construct this residual graph, and then you try to see, does there exist a path from y to x? It means we can send an extra flow from y to x augment, like via this path. So this is how it is done. Okay, so in this residual path, we found a path from y to x. What will we do now? After this, we will basically add this. Okay, we will add this to the our current flow. Okay, so we took this and we added this here. Right now, notice our flow has increased by 1. So there is like one path here, and there is one path here, and this is another. So every time flow will increase by 1, and if there is a cut of size at most k by max flow min cut theorem, you can only do this k times, right? And since because we are all we are doing is to find a BFS or DFS starting from y to x, we can do this in linear time, order m plus n time, because all we are trying to do in this directed graph, does there exist a path starting from a vertex in y and ending in x? Okay, so this is how you play around with your residual graph, and just by k steps of this algorithm, you are guaranteed to find either k edge destroying paths, or you can find a cut of size at most. Okay. Okay. So if we cannot find an augmenting path, we can find a minimum cut of size p. How can we find a minimum cut of size p? That's very easy. And there could be many. So you're starting from y, okay, you look at the reachability set of vertices that from starting from y, you can reach in the residual graph. And the set of edges leaving that is your min cut. For example, here, this is your min cut. Okay, and if you go corresponding, if you delete this set of edges, then you cannot reach x to y. Okay, and guarantee of equality holds for Menger's theorem or by max flow min cut theorem. Okay, so this is how we could find a min cut of size at most k in k into m plus n time, which is linear when k is fixed. So, but for our purposes, because all we will be looking for, does there exist a cut of size at most k or not, and this we can do it in order k into m plus n time. Okay, I hope this is clear. The reason why I went slightly quicker at this part, because this is something which you may have seen in your undergraduate algorithm course. Okay. Okay. So all we wanted to tell you from this, even if you did not understand the algorithm very well, is that an xy cut of size at most k, if exists, can be found in time this. So please take that. So this is our takeaway point. That an xy cut of size at most k, if exists, can be found in time order k times m plus n. Okay, that's it. Now let's move. So a notion which will be very important in combinatorial optimization and also in our lecture is what is known as the function delta is submodular, or the function. What was that function delta? If you recall correctly, the function delta was basically given a set R. It is a set of edges with exactly one endpoint in R. Okay, so the function delta is some. So recall. Okay, given a graph G, what was the function? The delta function was in fact r greater than equal to 0. What was the function? Delta of x, okay, let's call this function. So what was delta of x? Is basically number of edges emanating out of x. Okay, that's it. So what is the meaning of the delta function if submodular? So basically we need to show that if you look at two sets A and B, for arbitrary sets A and B, we need to show the contribution of A and the contribution of B is larger or equal to contribution of A intersection B plus contribution of A union B. Okay, and so this is a function satisfying these properties are called submodular function. Okay, so what is a function? Okay, so we can say a function from some say a function f from some universe to say r greater than equal to 0, okay, is called submodular if for any two arbitrary sets A comma B subset of U, f of A plus f of B is greater than equal to f of A union B plus f of A intersection B. Okay, so now we have to show that the set of edges, the cardinality of set of edges emanating some set in the graph is a submodular function. So this is what we will try to show next. Okay, so what I'm going to do to show this, we are going to determine separately the contribution of the different types of edges. So suppose this is A and B are there, A and B, they intersect with each other. Now where are the edges could be? So edges in my graph could be leaving A completely, leaving B completely. Okay, it could be going from A to B or B to A. It could be completely contained inside this, right? Right? So these are the kind of edges which could help us, or it could be edges like this. Okay, and let's see how they contribute to both sides. Okay, so first imagine that there is an edge which is leaving B, but it is going inside A. It is not contributing to the delta of A. So now what is the contribution of this? It is contributing to the partial of B here 1, but partial of A, or the boundary of A 0. But look at this A intersection B. It is contributing to A intersection B because it is going out from A intersection B to this. Okay, but it is not contributing to the partial of A union B. So an edges of this nature contributes one to the left hand side as well as one to the right hand side, and hence its contribution is proper. Okay. Now similarly, look at an edge which leaves from the intersection but now goes to the B side. Still, now it is contributing to the delta A side, but it contributes to the B side, and similarly to A intersection B, but not to the other. Great. What about an edge which leaves B, but it also its other endpoint is not in A, but then it contributes to A union B. Left hand side it contributes to the delta. So still the contribution of this edge to the left hand side is at least as much as its contribution to the right hand side. And similarly for an edge A leaving from here and going completely outside will contribute to the delta A and to delta union B. So left hand side contribution is still greater or equal to the contribution to the right hand side. Okay. Now what about an edge which intersects, which one vertex in the intersection and it goes outside? Then you notice that it contributes to both A and B in the left hand side, as well as it contributes to the both A intersection B and A union B in the right hand side. Again, the contribution to the left hand side is at least as much as its contribution to the right hand side. Okay. Now what about an edge which is like here? So now what is the meaning of this? So then this is an edge with endpoint in U and endpoint in V. So from the V's perspective, U is inside A. from the huge perspective, V is outside, but it's not in A because it's not in the intersection. Then again, it contributes to delta A and delta B, but it does not contribute to anything in the right hand side. Neither it is in intersection B, neither in A union B. And in this case, still left hand side contributes more than the right hand side. Okay, so this just tells us that the function delta is submodular. Okay, and now we will use this property of submodularity to prove an interesting property about the function. Let lambda be the minimum xy cut size. Okay, minimum xy cut size. Then there is a unique maximal R max which contains x, such that delta R max is an xy cut of size lambda. Okay, so now what is the meaning of this? Let's try to parse this. So here is my set. Okay, here is a set x and here is a set y, and lambda is the minimum x y cut size. But there could be many cuts, right? So what is the okay? So this is an x and it's a minimum cut. So it's also a minimal cut. So we can find a set R such that there are lambda edges leaving out. But there could be several such R's that will do the job for you. Okay. Now, what this lemma tells you that if you have two R's, say R1 and R2, okay, what this tells us that look, here is an x and here is an x and here is some R whose value is lambda, and of course this is a min cut, so y is completely outside, and suppose this is say R1 and there is another one which is x and say R2, number of edges going is still lambda, then we will be able to show that R1 is contained inside R2 or R2 is contained inside R1. Or in other sense, what does this lemma tells us? That there is a unique maximal R max that contains x. Unique maximal R max that contains x. So, right? So, I mean, so if there are two R's such that they are min cut, the number of edges going out is min cut, then one of them is contained inside the other, which implies that basically basically what it means. So suppose you took one which is contained inside the other. Now what about R2 and R3? Maybe it is contained inside R3, so on and so forth. So basically what I'm trying to tell you that if you say that hey, look at this R, look at this R, and what is the property that this contains x, number of edges emanating out is lambda, and y is outside. Furthermore, you can say that look, I cannot add any more vertex I cannot add any vertex y to R without increasing the cut size between x and y. Then such R is unique and we will call that R max. So let's try to prove this. Okay. So suppose, right? Suppose, okay. So suppose there are two R1 and R2 such that delta R1 and delta R2 are xy cuts of size lambda. Okay. So what I needed to show to you that, well, they contain each other. One of them contains each other, or yeah. So both are R1 and R2 are xy cuts of size lambda. It means, look at this R1 and R2 as a set of vertices. It contains x and y is outside. Because that is the definition of R1 and R2. What is the definition of R1? That it contains x, it doesn't contain y. R2 contains x, doesn't contain y. So if I take the union of R1 and R2, and then x will be contained inside the intersection and y. Now we know that the delta it's a submodular function. So now we will apply submodularity on the sets R1 and R2. Then what we know? Delta R1 plus delta R2 is at least delta R1 intersection R2 plus delta R1 union R2. Okay, but what is the value of delta R1 is lambda. What is the value of delta R2 is lambda. Okay, and now what is a value of delta R1 intersection R2, right? So what are I trying to? So look at this delta R1 intersection R2. What is the property of delta R1 intersection R2? This is, look at this R1 and intersection R2. This size, this part. What is R1 intersection? Even if I look at R1 intersection R2, it contains, so what is the property of, let's say, write down. R1 intersection R2 contains X, does not contain Y. It means the edges which are adjacent, it means delta R1 intersection R2 separates X from Y. It means the number of edges adjacent to R1 intersection R2 can only be more than lambda, because lambda is a minimum number of edges we need to delete to separate X from Y. And R1 intersection R2 is one separator. So number of edges that are adjacent to R1 intersection R2 can only be more than lambda. It cannot be less than lambda, which implies that delta R1 intersection R2 is also greater than or equal to lambda. Now left hand side is like what? 2 lambda is at least equal to greater than equal to let's say we can say if we do this computation, delta R1 union R2 is less than equal to 2 lambda minus delta R1 intersection R2. Now we know that delta R1 intersection R2 is at least lambda, right? This is greater than equal to lambda, which will imply that delta R1 intersection R2 is less than equal to lambda. So what we are able to found that look, I mean, they are not maximal in the following sense. They are not maximal in the following sense. They are like in the following sense, because there is some other min cut which consists of these guys, and it is still a min cut. Or in other words, let's try to see what we proved just now. So as I said before, okay, what is the meaning of maximal here? Okay, I wanted to say that look, here is an X and here is an R. Okay, we say that look, R is a maximal XY cut of size lambda, meaning there does not exist R prime such that first R is a proper subset of R prime, and second, let's say lambda of R prime is less than equal to lambda of R. Okay, there does not exist R prime such that R is subset of R prime, and also we should write, this is third point, R prime intersection Y is empty. Okay, such sets do not exist, right? Then we will call this a maximal with this property. Now what we have shown to you is that look, if this is a definition of maximal you are trying to put, then and you are only trying to put this maximal with respect to min cut size, okay, then there is unique maximal R with this property, right? So you cannot have two R1 and R2 with the property that look, I cannot extend R by other vertex such that the cut size still remains the same, because if that happens, then we could have taken R1 in union R2, which is a superset of both R1 and R2, and it is still disjoint from Y, and the number of edges which are going across, it's at most lambda, right? So if I'm going to call you that R max, some set R is maximal with respect to set inclusion for a minimum cardinality lambda, then there is a unique such set. That's all that this theorem proves. Okay. So what we proved is the following. Okay, that let lambda be the min cut size between x and y, then there exists a unique set R max, unique maximal set R max with delta R max equal to lambda. Okay. So in other words, what it says, okay, if you have some R1 with the property that X is subset of R1, Y intersection R1 is empty, or rather for every R, okay, such that what is the property? X is a subset of R, Y intersection R is empty, and delta of R equal to lambda. We have that R is a subset of R max, right? So any set as this has a property that they are contained inside R max. Okay. Okay. Now that also tells us an algorithm to find out how. Given a graph G and sets xy, we can also define the notion of R min and R max. What is R max? We'll talk about R min later. R min is the smallest set that has this property, in the sense that this is part of R min is part of every R that has a property. Okay. So first we will talk about R x equal. How can we find an R max? So you're given a graph G, sets xy subset of Vg, and we would like to find the set R max. How can we find in polynomial? Okay. So basically what you start with x and y. Okay. You compute a min cut. So suppose you computed a min cut here. Okay. Right. Then the moment you computed a min cut, you know that this set of vertices is definitely contained inside that R max you are consisting because of the property. Now what you do? Okay, fine. Maybe this is an R max. So maybe this is R max, or maybe it is not. If it is not, what we do to the current R, you add some vertex U and check, is the min cut increased, right? Is the min cut increased? So now what do you mean min cut increased? So you compute R union U comma Y. So this is where you will compute the min cut, right? Because you know that the min cut between R and Y is lambda. Okay. So now you take R union a single vertex, put them together and say, what is the min cut between this set and Y? If it is still lambda, then you know that Y, U is also part of that, because this set is contained inside that R max. Otherwise, you forget about that U and you try some other vertex. So the once you find a set R such that for every vertex which is outside, okay, for every vertex outside W, R union W comma Y, okay, has min cut more than lambda, then you stop and you can say that this R is our R max. Okay. So you iteratively add vertices to X. If they do not increase the minimum XY cut size, okay, a minimum XY cut size, then you stop and say, this is my R max. And what is similarly for R min? What is an R min? So first let's define what R min will mean. So what is R min? Okay. So one way of defining R min is that what we define R max. Okay. So let R min be a set such that first X is contained inside R min. Okay. R min intersection Y is phi. Okay. So what is the meaning of R min? Is set such that X is this, R min is this. So first of all this, and lambda of R min or delta of R min is equal to lambda. Okay. So rather than writing, let R be a set such that this happens. Okay. R is called R min if the following happens. Okay, or rather R tilde. A set R tilde is called R min if the following. Every R that, for every R that satisfy the above, we have that R tilde is contained inside R. Then such R tilde is called R. There are other combinatorial ways of looking at it. So for example, suppose let R1, R2, RQ be the sets such that they are XY min cuts. Then basically R max is nothing but union Ri's and R min is intersection Ri's. Okay, so this is how you can do this. And there is another way of making is this. Okay, what is this? So you look at the residual graph, okay, and you look at what is R min, those vertices which are reachable from X, and what is R max, those vertices from which Y is not reachable. Okay, what are R max? Vertices from which Y is not reachable. Okay, so R min, vertices those are reachable from X. Okay, here. So these are the vertices which are reachable from X. See, I can reach, yes, I can reach all these guys, right? And what is R max? Vertices from which Y is not reachable. Okay, so which are the vertices from which Y is not reachable? Well, I cannot reach from here, as well as I cannot reach from these vertices. I cannot reach, or these vertices I cannot reach, or these vertices I cannot reach Y, right? So this is basically R max. This is R max and this is R min. Okay, so this is how also you can make R max and R min. Okay, so I hope we have talked about important cuts, their extremal properties, and in the next lecture we will we will talk about now I'm going to talk about important cuts, and I'm going to define important cuts. So in the next class we'll talk about important cuts, define what they are and how many of them are there. Thank you.